Hello, would you like to learn the physics of splash? You can try this activity at your home by yourself. Have a bucket full of water and try to dip your arm in it. It is that easy. Now, try this one out. Hit your palm wide open and apply some muscular force and then again hit the water surface. Why does it hurt so much? Do you want to know the reason? Come, follow through this presentation and you will know why it hurts so much when you hit the water surface with your palm wide open, when it is so easy to just dip your arm inside. Hello, today I will be presenting the topic viscoelasticity. I have learned this concept from the paper published in 2010 in the Journal of Statistical Physics by Kurchin and his collaborators. The title of this paper is Do Solids Flow? I have chosen a similar title for this presentation. Are solids really solid? What we mean by this question in the title is, are there precise definitions or characteristic properties by which I can distinguish a solid from a liquid? High school physics teaches us that a solid and a liquid can be distinguished on the basis of the property rigidity. Rigidity is a property by virtue of which a substance can withstand shear stress within the breaking point stress limit. So a solid is a rigid, a liquid is not rigid. What happens if I apply shear stress to a liquid as it cannot withstand shear stress? So there is a flow in the liquids, and corresponding to this flow, I can calculate coefficient of viscosity. What viscoelasticity means is, it is a behavior for certain substances in which at certain time scales, the response of a system towards shear stress is like of an elastic solid, and at larger time scales, the response is like a liquid. There are only a few substances that exhibit this behavior, like liquids, gels, emulsions, paste, foams, and some other granular substances. Always we have to carefully quantify this time scale, and we will learn in this presentation how one does that. Viscoelasticity is interesting because it explains a very common instance that we might have noticed in our household. So if I hit a palm on the water surface wide open, then it hurts so much, while it is that easy to just dip a finger in the water surface and pierce through. We will see that why such a thing happens. So the author of the paper, Kurchin and his collaborators, asked two main questions. Can solid in general exhibit viscoelasticity? Second, is rigidity a time scale dependent notion? If we answer the first question conclusively, it means that second question is answered itself. Now, the claims made by the author are, rigidity is a time scale dependent notion. Solids are viscoelastic in nature, and for infinite simple shear stress, a flow is induced in the solid at larger time scales. Let us look at the calculations performed by the authors. Imagine a d-dimensional solid with equal side lengths. Now imagine a shear stress is applied to the system. This means with some shear strain, the solid deforms. A schematic diagram shows a two-dimensional solid with shear strain gamma and shear stress sigma. For an infinitesimal shear stress, the shear strain is very small, and since this small angle approximation holds here, the topmost corner point of this solid is displaced by the shear strain times the length of that solid. This means that each particle in the solid is displaced by the shear strain times the y-coordinate of this position of this particle. We know that shear strain upon shear stress is a constant, and shear stress upon shear strain is also a constant. This constant is given by G, which is shear modulus of elasticity. As in the earlier slide I mentioned, we are interested in calculating the free energy change of the system when it was deformed and when it wasn't deformed. So this change is given by this expression. This means that deforming a solid increases the free energy of the solid. Well, this is true. Why? Because energy is supplied to the solid by a mechanical method. Now, I apply the classical nucleation droplet argument. I imagine from the center of the solid, a cavity, a symmetric cavity of radius r emerges. And Within this cavity, all the particles are reshuffled in terms of their position parallel to each other so that these strained or sheared particles are unsheared or unstrained. Now I evaluate the change in free energy again. Before calculating this change in free energy, there are some simulation videos and pictures that will help us visualize the process better. So this is a two-dimensional hexagonal crystal with hexagonal unit cells, and we can see that this is a sheared hexagonal crystal. Now I apply the nucleation droplet and see what happens. So I can see that within a circular boundary, inside this boundary, all the hexagonal cells are unsheared, and outside this cavity, all the hexagonal cells are sheared. It is interesting to note that the colored portions in this diagram with blue and a similar color represent the mismatches between the sheared and unsheared cells or unit cells at the boundaries. Precisely, this mismatch increases the free energy of the system. This is a much larger system with more number of unit cells, and we can clearly see a nucleation droplet with a definite boundary. This is a video for different nucleation radius, and we can visualize how the nucleation droplet grows and the boundary effects emerge. We can see that as the nucleation radii increases, the boundary effects increase. So the change in free energy for the sheared and nucleated configuration versus the sheared without nucleation droplet configuration is given by this expression. The first term in this expression corresponds to the mismatches. This omega of sigma is a surface tension-like term. Now I calculate the extrema of this function delta f of r. It turns out delta f of r has a maxima at this r star point. This r star is labeled as critical radius. This means that from 0, as I increase the nucleation radius till it reaches critical radius, the size of the nucleation droplet increases and the change in free energy also increases. Once the new critical droplet condition is achieved, any further increase in the size of the droplet, so I calculate an upper bound for this free energy. This upper bound gives me the maximum free energy that a metastable state, such as this deformed and nucleated state, has to overcome in order to stabilize. We know that for a metastable state, there is a finite lifetime associated with it, which is required to jump from this metastable state to a stable state. This is given by the second expression tau star, where delta f of r star is the free energy barrier. Now, we have pretty much covered the entire process. We started with a d-dimensional solid which was sheared. Now this sheared solid was subjected to classical nucleation droplet argument. Once this argument is followed through, we learned that there is a finite time it takes for the metastable state to come to the original configuration. Now, if I continue to maintain the shear stress, then what happens? So if I continue to maintain the shear stress, once the metastable state has come to the stable configuration, it will again deform, follow through the same steps, and again undeform. This means that after certain period of time, the shear strain is again applied to the solid. So you can associate a rate to this shear strain, which are called shear rate. This shear rate, gamma dot, is given by the ratio of shear strain and this time scale tau star. This time scale is precisely the time scale that I use to characterize viscoelastic behavior. If I measure the response of the solid way lesser than this time scale, I will get an elastic solid-like behavior. And if I measure the response corresponding to this time scale at much larger time, I will get a liquid-like behavior. Since for a liquid-like behavior, there is a flow, and for that flow, I can calculate the coefficient of viscosity. It is calculated and given by this expression. Now, there are two possibilities. One, for a vanishing shear stress, the surface term also vanishes, and second, for a vanishing shear stress, the surface term doesn't vanish. In the latter case, it is clear that coefficient of viscosity diverges for sigma tending to 0, that is very small shear stress. Now, if the surface tension does vanish at infinitesimal shear stress, then we can always take the limit and renormalize these exponents. This again will tell us that coefficient of viscosity diverges with an essential singularity for vanishing shear stress, that means infinitesimal shear stress. What we can conclude from these are the characteristic behavior of solids cannot be distinguished from liquids that easily. Why? Because Kirchhoff claims that solids are viscoelastic, and the calculation followed through does implicate such behavior. Now, one has to calculate this time scale for each solid of interest, which this calculation will help us to calculate. Now, we can conclude the entire paper by saying that a solid will behave like a solid if I measure the response against an infinitesimal shear stress at much lesser time scales than time scale it takes for a metastable state to come to the stable state. And if I measure the response at way larger time scales than the time scale it takes for the metastable state to stabilize, is going to give me a liquid-like behavior. Well, this liquid-like behavior is interesting. Why? As we saw in the previous slide, the coefficient of viscosity diverges for vanishing shear stress with an essential singularity. But for ordinary liquids, this isn't the case. Viscosity is a finite quantity. Why? Because of the Newtonian linear relations in viscosity and shear stress. Well, this is what I wanted to present. Thank you.